All right, so hypothesis testing outside the basics 8.1. So we're going to do 8.2. So we're going to be testing claim about proportion. So testing claim about proportion. Now what's nice is when we test these claims, the way it's done for all of these statistics, no matter if it's proportion, if it's mean, if it's standard deviation or variance, you know, the steps 1 through 8 are all exactly the same. You're just using a different critical value and a test statistic to map that critical value. So with proportion, what we know is proportion, we're using a z distribution. So this is 0, so you know these are going to be z-scores. Negative z, positive z. Now, depending if it's going to be one-tailed or two-tailed, you know, we're going to use either, like if it's two-tailed, you know it's going to be z alpha over 2 and negative z alpha over 2. If it's right-tailed, you're going to use just z alpha because of the tails, which is the same as the alternative hypothesis. And if it's, you know, and if it's left-tailed, you're going to be using negative z alpha. So the idea is the area in the tail is always going to be equal to alpha. If there's two of them, it's going to be alpha over 2 plus alpha over 2, which is equal to alpha. If it's just one-tailed, it's going to be alpha. So, you know, in this case, this would be proportion is equal to some number. So let's say I just make up a number like 0.7. This might be like proportion is greater than 0.7. So this would be Yep, and this would be, say, proportion is less than 0.7. So, like I said, we'll use this kind of idea to set these things up. So, I'm just going to go through step 1, step 2, step 3, all the way up to step 8 with these. So, let's pick an even problem. Let's say, let's do M&Ms. So, number 12 on 8.2. So, number 12 says. It says in data set 27 in appendix B, what we have is we have a sample of 100 M&Ms, and we notice that 27 of those 100 M&Ms are blue. So that gives us a proportion of 27%. So that's where the 27% came from. 27 of these 100 were blue. So this is our sample statistic. This is our 27%. It says the Mars Candy Company claims that the percentage of blue M&Ms is actually equal to 24%. So what it says is use a 0.5 significance level to test a claim. Now, the last question, it says, should the Mars company take corrective action? Basically, are they saying, is their number wrong? Should it be higher? So the idea is this, is they claim that it's 24%. But what I did is I got a sample, and my sample actually there was 27%. So what they're doing is they're claiming equality, but the big question is 27% that far away from 24%? Now, intuitively, maybe you would say probably not. You know, they're pretty close. So the idea is, are these two values significantly equal? Or is this number significantly high? So in order to do that, we're going to have to, you know, we have to find our tails and determine if it lives in the tails. Let's see if it's significantly high or significantly low. So step number 1 says test the claim that Mars says that M&Ms, the proportion of M&Ms is equal to 24%. So the way we do this is we're going to go step 1. Step 1 is what's the claim? Step 1, well, the claim is that our proportion, let me write it this way. So the claim is that the proportion is equal to 0.24, so 24%. So then number 2, we have to do what is the opposite of that claim? So what's the opposite? So you're either equal or you are not equal. So P is not equal to 0.24. So step 3, what we have to do is we have to take these two equations and determine where they are. You know, what one's the null and what one's the alternative? So the null is the middle area. So this is like this is the null area. This is the null area. This is the null area, and our alternatives happen to be these tails depending on what they're asking. So I noticed that we're talking about equality. So we're talking about this particular situation. So let's take a look. So the null hypothesis is always the one that has the equal sign in it. So this one right here is our null hypothesis, that P is equal to 0.24. So that means the alternative is P is not equal to 0.424. So now these little colons basically means claim is this, opposite is this. So the colon is really just a shorthand for is. So I don't have equals here because I have an equals right here. It looked funny with the equals. So the null hypothesis is proportion is equal to 24%. All right, so now number 4 asks us to talk about alpha, like what is our significance level? Well, the particular example, it says to use a 5% significance level, 0.05. And actually, in this space right here is where I kind of I try to figure out, you know, its shape in the critical values. You're probably supposed to do that in six, but I like to do it here because it's a good spot to discuss it. So what I ask myself is this one-tailed or two-tailed? Well, your tails actually come from the alternative, because the alternative happens to be these shaded areas. You know, the null is the inside, the null is the inside, the null is the inside. So these shaded areas are the alternatives. So since this is a not equals, to be not equals, you could be too low or too high. So this would both represent not equals. So the not equals happens to be a two-tailed. Happens to be two-tailed. So since it's a two-tailed, what I'm going to do is I'm going to take this alpha and I have to cut it into two tails. So this is going to give me 0.025. So when I draw my little picture for number 6, we're going to do 5 in a second. So I draw my picture for number 6. Is what I know is I have this z distribution, and I know that we're talking about not equals. So you know your alternative is going to be here and here. So each one of these zeros is 0.025. This is equal to 0.025, and the null is in the middle. Remember, since these are z-scores, the claim represents a z-score of 0. So these values over here are critical values, you know, bordering, you know, what I consider significantly high and significantly low. So this is going to be positive z alpha over 2, and this is going to be negative z alpha over 2. So they're going to have the same number, just opposite inside. So we can find those z alpha over 2s. I guess we might as well do it now. So if alpha is equal to 5% and these two tails are 2.5, you can see that this is 95% here. The reason I like to show that is because when you use a z-score, you have to use area to the left. So, like your negative z alpha over 2, let's just do the positive z alpha over 2, because if I know this number, I know that number is negative. Okay. So, the area to the left of this positive z alpha over 2 is going to be the 0.95 plus 0.025. So, if you add those two numbers, you're going to get 0.975. So, looking on your z distribution, you can see that 0.975 is right here. And if you map this back, you're going to get 1.96 or 1.96. So this number right here, this is 1.96, and this number will be negative 1.96. All right, number 5 says, here we're going to do our test statistic. Well, our test statistic is our sample value. This comes from the sample, so this will be our sample value. So I want to know, like 0 represents your claim, so this 0 here represents your 24%. I want to know where that 27% lies on this curve, on this bell. So what I need to do is I need to find how 27% relates to the 0. So our test statistic is z, because these are z-scores. Z is equal to p hat minus p all over the square root of p times q over n. So p hat is the sample, p is the claim. So p hat is the sample, so 27% minus, remember you have to put everything in decimal land, okay, because we're going to have to put it in our calculator, minus our 24%, which happens to be our claim. Now you notice how none of these things have hats, because we center around the claim as opposed to the previous chapter where we centered around the sample. So that means this is going to be equal to 0.24 multiplied by 0.76, all divided by n, and n was equal to, I think it was 100, and it was equal to 100. So when you plug this thing into your calculator, make sure that you put parentheses around the numerator. So if you pop it in, this big giant division basically means that the top is grouped. So make sure that you group the top so the calculator sees that. So when I plug that in, I got 0.27 minus 0.24, close parentheses, divided by the second square root. The square root's going to group the entire bottom, so I don't have to worry about that. 0.24 times 0.76 divided by 100. So what I get is I get a z-score for this of 0.70. So 0.70. So we round it to 2, because that's what we do for z-scores. Okay, so what I want to know is how the z equals 0.7 relates to this particular number here. So this z equals 0.7 right here lands. Well, do you notice how it lands in between these two numbers? It lands in between this negative. It actually lands about right here, doesn't it? It's about, this is about 2 standard deviations above, so it's less than 1 standard deviation. So that right there is that z is equal to 0.70. So the question is, where does it live? Does this value live in the null, or does it live in the alternative? Well, since it lives in the null, which is the middle, we'd say 7. We'd say, well, we have 2 different statements. You either reject the null, which means it lives in the alternative, or you fail to reject the null, which means it lives in the null. So we're going to fail to reject the null. So that's just stat talk. Fail to reject null. Basically, this is like a stat way of saying that we accept the null if we fail to reject it. Kind of like that disjoint statement, like the not joint thing. Ridiculous, but it is what it is. Okay, so what I'm going to do is, and we'll come up with a statement about, because I want to know if the claim is correct. So what we know is that this 27% is above this 24%. You can see that. The 27% landed above the 24%, which it should, because 27 is bigger than 24. But the idea is it high enough to be considered not equal? Well, this whole area, the null area, is kind of like the area of equality. So really the 27% is actually statistically equal to the 24% using this critical, using this significance level. Maybe if I went 0.01 or 0.0001, like I should actually make it bigger, I apologize. So if I use like maybe 0.1 or 0.2, if you only want to be like 80%, if you want to like shrink these, eventually I can find some z-scores to where it fail, but really most of the time we use like 95% confident, or significance level of 5%, or 99% confident, and so on. So using this significance level, these 2 values, this 24% and 27%, are significantly equal. So what I'm going to do is, since we failed to reject the null, I'm going to go up here. I'm going to say, well, we failed to reject it, so we consider that thing correct, which means that this thing is incorrect, right? So if this is correct, let's see where this maps to. Where did this number come from our original 1 and 2? Well, this actually is this, right? So if this one is correct, then that means this one is correct, and this one is wrong. So is the claim correct? Yeah, the claim's correct because the claim is the null, because I live in the null. So then we go back to our statement. So I'd love to just say there's enough evidence to support the claim, and that actually might be the statement, but there's like 4 different ways we say this, and it comes back to 8.1, so I'm just going to show you what this is, and then we can map this accordingly. So our 4 statements live here. So basically we have these 4 conditions, and you look at the very first statement to figure out where we're at. So the original claim does not include equality. No, our original claim does include equality, so we're not here or here, we're over here. The original claim includes the equality. So you can see that my claim includes the equality. So that means I'm either here or here. Now, I either rejected the null or I failed to reject the null. Well, I failed to reject it. So the original claim includes equality, and I failed to reject the null. So the way we actually say this is we say there is not sufficient evidence to warrant rejection of the claim, which is basically saying the claim is true, but in the words that they want. So this is the type of statistical wording. So there is. So number 8, there is not enough evidence to warrant rejection of the claim. So we're not rejecting it. So another way is the claim is true. Let's do that. How about malpractice? So number 14 says a study of 1,228 randomly selected medical malpractice lawsuits. It was found that 856 of them were dropped or dismissed. Seems kind of a lot, doesn't it? But let's keep going. So it says use a 0.01 significance level to test a claim that most medical malpractice lawsuits are dropped or dismissed. Should this be comforting for physicians? Well, if a lot of them are dropped, then probably. Okay, so what we're going to do is we're going to test the claim. So let's talk about the claim. This is kind of perfect wording because they like to do this stuff. So number 14, 1. So let's talk about the claim. And then 2 is going to be talking about the opposite. All right, well, if we look at the claim, what we can see is that it says the claim is that most medical lawsuits are dropped or dismissed. Now, what most means is the majority. So if the majority are dismissed, we're talking about bigger than half. Strictly bigger than half, because it was equal to half, and that wouldn't be the majority, or that wouldn't be most. So most means bigger than half. So that means most means that the proportion is greater than 0.5. Wow. I'm filming over here. Holy cow. Did it get stuck? I'm going slow. Okay. All right, so different than before. All right, so number 14. So that's the claim. So that means the opposite has to be, well, you're either greater than or you're less than or equal to that 0.5. So then we go to number 3 and we talk about the null hypothesis and then the alternative hypothesis. Well, the null hypothesis is the one of these that have the equal sign. So this is going to be P is less than or equal to 0.5, and then the other one is going to be P is greater than 0.5. I'm sorry, 0.5. Now, depending on the book, some books actually just drop this. Instead of writing that, they might just write P is equal to 0.5 as opposed to P is less than or equal to 0.5. And I won't mark you either way. So, use this one or this one depending on what the book actually uses. I think our book does this. But some books actually just leave it that way. And it's fine. It actually doesn't change anything as far as what is the outcome. So I think the idea they do this is the null is the equal part, so that's why we really kind of get to that. So it's up to you. This one or this one. I don't care. All right, so number 4 says, well, alpha is equal to 0.01. So what kind of tail do we have? Do we have a two-tailed, a left-tailed, or a right-tailed? Well, remember the tail actually comes from the alternative. Let me scribble this out. It's kind of messy. So the alternative P was greater than 0.5. So the alternative is P is greater than 0.5, so that means I have a right tail here. So this is a right-tailed. Notice how this points to the right, so this is a right-tailed. I forgot to tell you about p-value. I'm going to have to come back to that in a second. So this is a right-tailed. So since it's right-tailed, I'm only going to use one tail. So I'm going to go down here and have a look at number 6. So since it's a right-tailed, what we have is we have this particular piece right here. So our right tail is going to be this area right here, which happens to be 0.01. So I'm going to find this critical value. So a lot of times I ask, is it Z alpha or is it Z alpha over 2? Well, it's Z alpha because I haven't cut this in half. There's only one tail here, so this is 0.99. If it was two-tailed, I'd have to cut that in half. So then I'd ask, well, is it Z alpha or Z alpha over 2? Well, you'd say it's Z alpha because it's just one tail. Now, is it positive Z alpha or is it negative Z alpha? Well, positive Z alpha because it's over here on the positive side. Since it's a greater than, this is going to be positive Z alpha. If it was less than, it would be a negative Z alpha. So this is positive Z alpha. All right. Now that we have that, we might as well find it. So what we're going to do is we're going to look at area to the left of this number. Well, since this is one tail, the area to the left is this 99%. I don't have to do any other adding because of that single tail situation. So what I'm going to do is I'm going to go to the table, look at the body of the graph, and look for 99%. So over here, 99% is right somewhere. Right here. 9901 is the closest we can get. So if you look at this, this is 2.33. So this number maps to 2.33. So this is equal to 2.33. All right, so number 5, I'm going to find my test statistic, which represents, where does that sample live? So remember what the sample was, is we had, in this particular situation, we had, there were 1,228 total, and 856 of them were dropped. So our test statistic is p hat, and p hat is going to be the proportion, so it's going to be this 856 divided by this 1228. So what I know, our test statistic, so our p hat is going to be equal to that 856 divided by that 1228. Let's make sure I get the right numbers. Yep, divided by 1228. So this is equal to, you're welcome to use the exact number, and I'll probably try to recommend that, but most of the time it doesn't matter. So if you want to go 856 divided by 1228, sometimes they ask for a more accurate number. So maybe I'll take this all the way to 6971. Maybe that'll be good. That'd be good enough to not mess this up. So 0.697. Technically, I would, you're supposed to really go to 4 anyway. So, well, yeah. Actually, you're supposed to go to 3 because this is discrete. But bam. Okay. So just so I don't have any rounding errors. So z is going to be equal to p hat minus p all over the square root of pq divided by n. So p is going to be this 0.6971 minus my claim, which is 0.5, bigger than 0.5 because this number comes from the claim, divided by square root of 0.5 times 0.5, all divided by the total, which is this 1228. So, not forgetting to put parentheses around that. So this number is going to be equal to actually I can do it this way. Let's grab that number. Minus 0.5 divided by the square root of 0.5 times 0.5 divided by 12.28. So what I get is I get 13.81. Holy smokes. 13.81. Remember, that's a z-score. That's a z-score. That is, how many standard deviations does that represent? Well, a z-score represents how many standard deviations, right? So this is almost 14 standard deviations above the mean. So 1, 2, 3, 4, so 1, 2, 3, yeah, so it's way, man, it's like way out here. So it's way over here. So I'm going to do like a little broken, like, graph. So what I have here is way out to the right, that test statistic right here, this 13.81, landed way out here, 13.81. That was that test statistic. So how do these numbers look compared to each other? Well, the way they look is that this clearly is inside this alternative hypothesis. It's in the tail. So since it's in the tail, it's actually greater, since it's, well, let's kind of go here. So number 7, let's talk about it. So am I going to reject the null or fail to reject it? Well, since this lives in the alternative, I am going to reject that null. So this is going to be reject the null because it doesn't live in the null. So reject the null. So if I go back over here, I'm going to take the null, which is up here, and I'm going to reject the null, which remember came from this, right? So that means I'm going to reject the alternative, right? I'm the opposite. I'm going to reject the null, so that means I'm going to reject the opposite. So that means this thing is correct. And remember, that thing came from here, so that means the claim is correct. So remember, they were saying, are we actually bigger? Yes, we're bigger. We're way bigger. We're like way bigger. So so they did ask, how do doctors probably feel about this? Well, they probably feel pretty happy because technically, yes, most claims are dismissed. Think about it. What I mean by most is it's bigger than half, right? And remember the number? It was 856 all over 1228. It's like 70%. So 70% is like way bigger than 0.5. I wonder why I have so many standard deviations. All right, so number 8. So let's take a look at how we're supposed to read this. So go back to 8.1 and talk about the wording. Make sure you guys see how to map this. So what we know is 8.1 says, well, the original claim does not include inequality. That's correct, because the original claim was bigger. So it does not include inequality, so I'm either the first one or second one. And I rejected the null. Yeah, so I'm number 1. So there is sufficient evidence to support the claim. So we use this one. So sufficient evidence to support the claim. Okay. All right, let's talk about the p-value method real fast. So this is what's called the critical value method, which is what I actually prefer. But just because I prefer it doesn't mean that we're not going to learn both of them. So going back to the previous one. Well, two things that we can do. We can actually look at we can investigate these critical values, right? We can investigate these numbers and see where we live. Or I can investigate areas. What I know is this is going to be the right. If we look at the area of this thing, what I mean by that is our test statistic looks like this. So if I look at this area right there, so this is your p-value. If I look at that p-value right there, what I have to do is I have to go to, how you find this area is, remember, this is a z-score, so I know how to find the area to the right. So what you do is you go over that negative 0.7, and what I get is I get 2, no, it's not 0.7, it's positive 0.7. So what I get for positive 0.7 is 758 0, right? So that means this area to the left is 7580. So that means the p-value, our p-value, is equal to 1 minus that 0.7580. So 1 minus 0.7580 is going to be equal to, oh, that's wrong, is going to be equal to this. So what I get is I get 0.24, so this is equal to 0.2420. And what we notice is that this p-value is that p-value is bigger than the significance number. So instead of investigating these critical values, what you can do is you can look at this, I apologize, it's not this number, you have to use alpha over 2. You have to look at this number right here. So if you look at those two numbers, you notice how this number is bigger than this number? Therefore, if it's bigger, that means it's outside the tail. That means it lives in the null. So that's how that actually works. So you can either use their areas or you can use their critical values. If we did the same thing over here, if I look at the area of this thing, you know that this, on my table, it's bigger than 3.45, right? So anything bigger than 3.5 is going to be 0.999. So remember that this would be 1 minus that number. So I know that that area right here, this area is going to be 1 minus that 0.99, so this is 0.0001. And what I notice is if you look at this number and you look at this number, these areas, that this area is less than this area, so it lives in the tail. So another way to show that it's in the alternative. So you can either look at these two numbers, or you can look at those two areas. So this is the p-value method, and this is the critical value method. And they'll both give you the same thing. So let's do one that's less, and that'll be it. What's nice is if you can do this for proportion, all the other ones are the same. You're just using a different equation for your test statistic and then a different distribution, so therefore a different table. So the last one, let's do the next even one. All right, so next even one is... All right, so drug screening. It says a company drug test success provides one panel THC test for marijuana usage. Amongst the 300 tested subjects, results from 27 subjects were wrong, so either a false positive or a false negative. But either way, they both represent wrong. False positive means that you didn't use it, but you tested positive, and a false negative means that you did use it, but you tested negative. So in both cases, they're incorrect. So use a 0.05 significance level to test the claim that 10% of the results are wrong. So what we're going to do is we're going to build this step. So number 1 says they want you to test the claim that less than 10%. So for number 16, number 1 says that the claim is that P is less than 0.10. So number 2 means that the opposite is going to be P is greater than or equal to 0.10. So number 3 means my null and my alternative. So the null is the one that includes the equality, so it's this one. So P is equal to 0.10. You could either use this or you can use this. I think the book just takes it straight to equality. But if you wrote it that way, who cares? It's not going to change anything. And the other one is going to be P is less than 0.10. I'm just going to do some quick mappings just to see where they came from, okay? So the one that includes the equality goes to H0. Number 4, they ask us for an alpha of alpha is equal to 0.0. So I'm going to go down to number 6 and start drawing my picture. I like the picture first. So what I know is that this is a left tail because the tail is always determined by the alternative, so this is a left tail. So that means we're going to use alpha or alpha over 2. Well, since I only have one tail, we're just going to use alpha. So that means this is going to be my left tail, and this is equal to 0.05. So that's what alpha is equal to. So now what I have to do is I have to find this value right here. So finding that value right here, well, remember this is, well, the question is, am I going to use Z alpha or negative Z alpha? You know, is this number going to be positive or negative? Well, you know that this is 0. The claim is 0. Remember, when you take this proportion to a Z value, that, you know, you're centered around this particular number. So 10% means a Z value of 0. And you'll see that if in the test statistic, if you plugged in the claim, you'd actually get 0. So this is going to be a negative number. So I actually like to say, well, this is negative Z alpha. So area to the left. Well, area to the left actually happens to be alpha in this case. So going to our table, we're going to look at 0.05, and when you look at that, it's immediately going to be a negative number, so it's kind of convenient. So 0.05, remember, just 1 0 past the decimal. 0.05 is right here. Spot on this spot right here. So 0.05, and if you map that down, what I get is I get 1.645 in the negative. So this is negative 1.645. All right, now number 5. What I need to do is I need my test statistic. So Z is equal to P hat minus P all over the square root of PQ divided by N. So I need to know what my P hat is. Let's do the work over here. P hat. Well, P hat was 27 over 300. Yeah, it's 27 were incorrect over 300, and if you do that, you get 0.09. So here's kind of the interesting part: is what we have here is they're testing the claim that less than 10% are wrong. Now, intuitively, you can see, well, 9% is less than 10%. But remember that it needs to be statistically different. It needs to be low enough to really be considered less. So is 9% less than 10%? Yes, but is it far enough to be considered statistically different? I don't know. I'm not really sure. It actually kind of depends on the standard deviation. It depends on essentially on n, really. So it depends on the standard deviation. So if n is big enough, it might be. If it is not, it might not be. So we'll see. So what I'm going to do is I'm going to plug that number in. So this is going to be equal to 0.09 minus 0.10, all divided by the square root of, remember this comes from the claim, so 0.1 times 0.9, all over 300. Again, don't forget parentheses up here. So I have 0.09 minus 0.1 divided by square root of 0.1 times 0.9 divided by 300. So what I get is I get a negative 0.58. So this is Z is equal to negative 0.58. And if I look at that, negative 0.58, I did it right. Oh, well, negative 0.58 lives right about here. So this Z is equal to negative 0.58. And what we can see is that it doesn't live in the tail. It actually lives in the null. It lives in the null. So number 7 is what we do is we fail to reject our null. So I fail to reject it. I'm going to go up here. So if I fail to reject the null, I'm going to fail to reject it, which means the null is correct. So I'm going to circle that, and I'm going to get rid of this part. So if I circle that, that means the opposite has to be true, which means the claim is incorrect. So the claim is wrong. Now let's see how we say the claim is wrong, because there's some wording for that, right? So back to the wording. So back to the wording. What we have is it says right now the original claim does not include equality. The original claim does not have equality. So the original claim does not include equality. So we're in the top 2, and we failed to reject the null. So we're number 2. So there's not sufficient evidence to support the claim. So not sufficient. Now remember what that means is we already know that 9% was less than 10%, but it's not small enough. You know, it's smaller, but it's not quite small enough to consider not statistically equal. So that's why there's not enough evidence to support the claim. And that's it.